Hello, everybody. I'm Mathieu. I am an instructor at Yashar University, and I will be hosting you for this meeting, and especially hosting Jonathan for explaining to us the work he's doing on mycelium. So I'm really happy that Jonathan is here tonight. I mean, for us, it's tonight, but for you, good morning, Jonathan. Because Jonathan is in Texas, as I remember.
Kansas.
Kansas, pardon, sorry. In
Not
Kansas, I didn't read properly.
Okay.
In Kansas, so it's a bit far away from us, but thanks to the technology and the pandemic, we are here to speak together tonight. And he will also especially show us some work he has done on mycelium and speak about the work I've seen from him, this vault he has been doing, and he will explain us how he did it and what are the challenges to continue to build with mycelium as an architect or as an engineer. So thanks a lot, Jonathan, for being here, and thanks to all of you to be here listening to this presentation and conversation at the end.
Yeah, well, thank you so much, Mathieu, for having me. Yeah, it's a pleasure to be able to share this. And indeed, the current situation has made it so that communities can be made at further distances, and so I think this is great for us to make a new community of people who are talking about this. So I'll share my screen to begin with. There we go. So my name is Jonathan Dessi-Olive. I'm an assistant professor at Kansas State University. We're very literally in the middle of the United States. If you were to draw an X in the middle 48, we're in the very middle. I'm about 2 hours away from Kansas City, maybe 10 hours from Chicago, right in the middle of the country. So I'm trained as an architect. I'm not a scientist. I'm certainly not a mycologist. But my background is purely in architecture, and I, at least during my education, focused specifically on construction. And I'll share a little bit of my research, the past research that I did, and the things that led me to this material, which is maybe not so new anymore, but in the context of architecture is still perhaps a little mysterious. So I hope to today tell you a little bit about the material itself, but also how I use my architectural knowledge in this context in order to try to invent new ways of building. So to that point, why would we need new ways of building? So let's start with just a little bit of maybe philosophy as to why I use this material. It's a bit of a strange thing, saying to grow architecture versus to build. So I'll begin with an observation. This is my own, and it is that in the current building culture, the lifespan of buildings is rapidly decreasing, while more than ever the global construction industry still primarily uses materials that are rather permanent. Now, I like to talk about these two buildings at the same time. And I've chosen the Georgia Dome in part because I did a fellowship in Atlanta at Georgia Tech. And that building, the Georgia Dome, which was constructed for the 1996 Olympics, it was demolished 1 month after I moved to Atlanta. And it had a wonderful tensegrity roof, a tension and compression element roof. Really a wonderful building, and it was torn down 25 years after it was built. Right, so it's living a bit the life of a rock star, I suppose, dying young. On the other hand, you have the Pantheon in Rome. It's a building made of concrete, very much like most of the stadium. It's a building that, like an Olympic stadium, people from around the world go to it. The difference between the Pantheon, though, is that it has cultural significance beyond the Olympics, and it has lasted 2,000 years. So I think we have to ask ourselves, when we're using this much concrete, which is valid when you're talking about buildings that are rather permanent, but when buildings like the ones that are being built, particularly in the last 100 years, if they are only lasting 25 years, 30 years, but being made with materials to last 100 or 200 or even 2,000 years, we have to begin to question, I think, the way that we build. And the truth is that this is a problem. Buildings are dying young. In the United States, we have a whole collection, in fact, of these inflatable stadia that have died, have been demolished within 40 years. And this is a common trend. The contribution of my country in terms of landfill waste is in the order of 600 million tons of construction and demolition waste in 2018. And this is, this is only going up. And so I feel like there is an urgency because concrete use is on the rise. It's the next most used material after water. And we are not really slowing down our use of concrete. Meanwhile, there are the aftermaths, or the we're feeling, I suppose, the effects of climate change now. And at least in my country, in the West Coast, we're having fires that are ruining places. If you look here, there's a fire in 2018 that destroyed 18,800 buildings. So whether or not those buildings were all being used, it doesn't matter. That means that there's a lot of work for architects to do. And I think we have to ask, how are we building in the face of these challenges? Even just in the last year, we're finding that we have to change the way that we work in the environments in which, and change the environments in which we work. Universities around the United States, at least, were building inflatable structures using plastic materials to make temporary structures. And we have to wonder, if something is so temporary, or expected to be, why use materials that are permanent? Or if the condition of pandemic is a permanent condition, how do we have to change how we build? So this is a very big question. And for me, this is one that has always sort of been at the front of my thinking, and has been the motivation for not only learning to build, but beginning to ask questions like this one, big questions, difficult questions, about what we are doing when we build architecture today. So I will focus on this pavilion later on in the talk. It is made of fungi, so mushrooms. In fact, the same mushrooms that you and I can eat. They are an edible mushroom. And the mushroom is actually holding together agricultural waste, things like hemp or corn or wheat, anything that is a waste product from the agricultural food industry in particular, can be used with this process of using the mushroom like a glue. So what we're talking about here is something called mycelium. And to be clear, it is the root of fungi. And the mushroom, that thing that we eat, the thing that you find on the ground, and yes, there are some dangerous ones, but there are a lot of really good ones. The mushroom is the fruiting body, or is the reproductive organ, actually. So we're not interested, at least in this context, we're not interested in mycelium, or we're not interested in the fungi as much as a reproductive body, nor as a food, but actually as a binder, as a network of what are called hyphae. And so these little hyphae, which come from the spore, make a web. And I have a little video that you can see. So mycelium, it begins with a spore and it begins to branch. And mycelium in the end is everywhere around us. It's underneath the ground, the trees, it's underneath the grass, everything. Scientists will describe the earth as actually having a mat, like a big mat of mycelium underneath everything, connecting all of our forests, our waterways. The largest living organism in the world is a fungus, and it lives on top of a mountain in Oregon on the west coast of the United States. It's something like 5 kilometers wide or something like that. I mean, it's like really big. And so in the end, mycelium is actually what sustains the planet in many ways. It links everything underneath us. It's integral to the way that our environments grow and thrive. They help distribute nutrients between trees and other plants. They also decompose in order to make other life possible. Now, that's all very exciting, but in our context, we're trying to control the mycelium as much as possible in a monoculture. So a single organism to make a single kind of material growing in its food source. And we're using its food source primarily as a mass. And so for us as architects thinking about building materials, at least for many who are interested in this material, we see it as a means of decarbonization through sustainable materials that take agricultural waste, something that is not favorable in certain industries, and making it have value. So we grow these entangled networks of hyphae. This is these white things that are growing in the image that you're seeing here. And we grow them around agricultural byproducts, as I said, hemp, corn, and almost anything that grows that is made of cellulose and contains lignin is going to be a favorable material in this context. Now, mycelium as a material is commercialized. It's patented. People are making extreme amounts of money off of this material, selling it to consumers. It has been tested extensively for its mechanical properties, but as well as its insulation value. Its acoustical properties have been explored a little bit. We also know that it has termite resistance, that it has mold resistance, and in fact, it has some fire resistance as well, at least enough to compete with many of the materials that we use day to day. Now, as consumers, I think in Europe you can get some from a company called Grown Bio. I believe they're in the Netherlands. So I think you could actually order some there. As a consumer, it will come looking a little bit like this. So it will be a dehydrated bag, and it will look like, you know, farm waste. And you say, why did I spend so much money on this farm waste? So you introduce water and just kitchen flour, the stuff that you bake with, wheat flour. And in a matter of 5 or 6 days after introducing that into the bag, you have a material that you can then pull apart, put into a mold, grow for an additional 5 or 6 days, and you can have an object that is in any shape that you make it, really, in the end. It's like casting concrete or plaster or anything else. And what's amazing is that there's very little energy that is needed in this case. Mushrooms need darkness, they need humidity, and they need oxygen. That's about it. So you don't even need electricity to make this thing happen, which is rather wonderful. And so it is this very strange stuff, but people have been working with it for quite a while now. And at least for almost a decade, people have been making things like furniture, lampshades. A brilliant young woman made a canoe. So she took this little boat and just, I don't know how long it lasted, but she made it. It's actually rather remarkable. A number of academic projects have made things like modular brick systems, acoustical panels, and in fashion in particular, there's quite a race to make fabric products that approximate the qualities of leather. And so rather than raising cow, that we could actually grow our leather-like products. There's quite a bit out there. Now, in the context of architecture, however, I think it's important to kind of bring it here quickly. So the notion of myco-architecture, so mycelium architecture, was actually coined, it's the term that was coined by an artist, Philip Ross, in 2009. He was interested in mushrooms. He'd been growing them a little bit, and it occurred to him that that block from which the mushrooms grew, that he could just use that as a building block. So he made an art installation, I believe it was in Germany, back in 2009, where he built this little vault in the shape of a catenary. I'll talk about that shape here in a little bit. More famous than that one, perhaps, is the effort by David Benjamin, the Hi-Fi, which is a tall tower that stood for between 3 and 6 weeks in New York City back in 2014. Now, this one was made with 10,000 mycelium bricks. The entire industry of how to make mycelium materials had to be elevated just for this project. The ability to grow this much material and produce this kind of a building block never existed before this project, and this project was actually essential to the work that happened after that. And so since 2014, we see numerous pavilions now using this material in many different ways. And some are perhaps more structural than others. I would say certainly the structure by the Block Research Group here that was displayed at the Seoul Biennale in 2017 is probably the most structural. These ones down here by Carlo Ratti are also quite good. They were in Milan 2 years ago. These other ones here are using mycelium as a unitized item, but perhaps less for structure and more as an enclosure kind of system. And so where do I fit in? I want you to take note that, at least with perhaps the exception of this one here down in the bottom right, that all of these structures are made with a unit based. A brick or a block makes the structure. Okay, so my background is in building, actually with bricks. And so, I took interest in these structures. I mean, with extremely, right? This made a lot of sense to me. And in fact, I knew I could build something like that. But as someone who was, through my academic career, and in particular in my postgraduate studies, learning how to ask research questions, I looked at the field of people who were making pavilions and said, well, what isn't being done? It's a new material, so to speak, and what has not been done. And the answer to that was that it hadn't been used like concrete. It had been used like concrete block, but it had not been used like concrete. No one had cast an extreme amount of material all at once to make a structure. So structures had been proven. There was no question that a material so weak, made of straw, essentially, could actually make a structure. Now, my confidence in the ability to make a structure like that comes from my work in masonry. This is it's a compressed earth vault structure that I displayed at the Venice Biennale in 2016. And it was really a kind of an entire demonstration of, say, my philosophy and my approach to my work in construction. The first being that I learned from history. I look and I actually build historical structures as a means of trying to think about ways of building in the future. Now, I don't just study them, I actually build, because I believe that validation through construction itself, is essential in order to make progress and to change minds of people who are perhaps resistant to changing the ways that we build today, or with what materials. The next is to compute efficient forms. So history can teach us about efficient forms because there were technological limitations. And if we can take ourselves back to those limitations, understand them as opportunities, there's actually quite a bit that we can do to change the way that we build for the better, to use less material or to use more sustainable materials, such as earth, or indeed, what I'm talking about, to use mushrooms. Now, renewable materials are essential, of course, to our future. And in the context of masonry, I've really tried to push the limits of what has traditionally been used. Stone and brick are wonderful, but they both require extraction of some kind of a material, and extraction of a resource that is perhaps quite limited. At least in the case of concrete, we know we're running out of sand. At a global level, we're running out of sand. And so we need to find something that is renewable to build with. And the last one has been most important to me in the last couple years, which is to assemble diverse collaborations. Now, I consider myself a builder or a craftsperson, at best a designer, and almost not an architect, definitely a researcher and an educator. But what I have found is that it's through working with people who do things that I don't know how to do that I can get quite a bit more done. And so I have gotten a lot done over the last years. This is a little less than a decade of work. You're seeing, at least at the top left, work that I was doing as a graduate student. And in the bottom right, a pavilion, an inflatable tensegrity pavilion that I made 2 years ago, right before the pandemic hit. And so there's certainly a trend in this work. There is a close study of history and historical forms, but immediately a departure into alternative materials, whether it's the use of earth, lightweight concrete right here, which I'll talk about a little bit later. But certainly this move to lightweight materials, whether they are using air or to use this material, mycelium. Now, within the course of that work, I would say the most important part of what I did early on as a student to motivate myself is to study this history, and in particular, the history of the Raphael Guastavino company. So if you don't know the Guastavinos, they are a father and son team. They came from Valencia, Spain, and they emigrated in the late 1800s to the United States, to New York City. And he came equipped with basically knowledge of a historical construction method, which was very common in Spain and, in fact, all around the Mediterranean, which is that of tile vaulting. And I'll describe that a little bit more in a second. What is amazing about the Raphael Guastavino company is that through the translation of historical techniques in a contemporary context, and in particular in the United States, he was able to make some of the most structurally daring masonry structures ever built on the planet. They developed decorative techniques that are unique in the American building arts. They worked closely with architects to develop essentially a monopoly on this construction system across the United States, building vaults in almost 1,000 buildings within a span of 40 years. They held patents on construction, which protected them and protected their use of their techniques. And many of their buildings are found in very significant buildings in the United States. And so what you have is this incredibly rich tradition of historical techniques being used in the United States at a time when most buildings were made of wood and were burning down like crazy. So the Guastavinos stepped in with a fireproof system that ultimately comes from as far back, at least on record, we know that the oldest known building that uses the same technique of using thin tiles actually dates back to the 1300s in Valencia. And so the Guastavinos aren't doing anything that crazy. They're using multiple layers of very thin ceramic tiles. The initial layer is laid with gypsum or plaster of Paris. It's a very rapid setting mortar where they can almost glue bricks to one another using very little formwork. And so it's very quick to build. The next layers, the second, third, fourth, or even more, depending on your span, are laid then with concrete. This was a major innovation in terms of Guastavino's use of the system. Previously, lime or more gypsum was used. But in the context of the United States, where in the early 1900s, right when the Industrial Revolution was going quite strong, concrete was available there more than almost anywhere else. And he was able to use, at that time, an innovative and new material in his traditional construction method. And in the end, what he makes is a construction method that is very quick. It requires almost no formwork, so no scaffolding or additional materials, mostly, to build. Extremely lightweight and strong, formally flexible, and of course, most importantly, in his context, fireproof. And so, how do you start to make something new? This construction system did not exist prior to Guastavino in the United States. It is truly an immigrant's import, right? An immigrant imported this thing, and very importantly. So how does he go from building, there's none of them anywhere in the United States, to 1,000 of them? How do you do this? So I think this picture basically explains that. And it is this point about making to prove your concept. Here, what you're seeing is approximately a 4-meter span made with only a few layers of tile being held by, I can't do the conversion. It's probably something like 50,000 kilos. And so, of course, you know, when you're trying to build a building and it's the early 1900s, I think this photograph says, where does it say? Yeah, August 1900, right here. When it's 1900, there are no building codes and nobody trusts you because you're a Spanish immigrant. The only way that you can convince them to let you build vaults is to do something like this. And so, in my own work, this is something that I try to replicate. Maybe not necessarily putting 50,000 kilos onto my structures, but at least to build them to prove that something is possible. And doing so is incredibly powerful because through practice, through repetition, through iteration, the Guastavinos put their vaults in some of the most important places across the country. If you ever get a chance to go to New York and Grand Central Station and you're hungry for oysters, you can enjoy really wonderful oysters underneath these beautiful vaults. If you were an immigrant in the early 1900s in the United States, you came through this building at Ellis Island. This is the Registry Hall. Every immigrant for quite some time came underneath a tile vault made by a Spanish immigrant. It's really rather significant, and it is because of the expertise in their way of knowing how to build that they were able to do this. Now, I want to stress, however, they were not the only ones doing this. Corbusier used this in a very strange but very interesting house in France in 1951. If you've ever been to Cuba, you can go visit a wonderful but a little bit dilapidated site that uses the exact same construction method for a number of schools, art schools that are there, commissioned by Castro. In Egypt, Hassan Fatih uses a very similar method of using thin brick, in this case made of compressed earth, and using them in a slightly alternate method called the lean brick method, which is more well known, at least in the Middle Eastern regions. But of course, this is not something that has died. As recently as 2010, earthen materials were used in South Africa to make these very vaults. Now, why am I talking so much about vaults? I should be talking about mycelium. The reason is that the principles of vault making apply to everything else, especially materials that are quite weak. And we know this because of the properties of unreinforced masonry, which is that they only work in compression. Stability is actually determined more by a geometry than by the material strength. So this means that even if you have a very weak material, if you can put that material in space exactly, or almost exactly, in the right shape, then you'll be okay. And historically, this has been done for, well, so we know at least 2,000 years because the Pantheon is still with us today, and is proof that putting material in the right place in space can really do something. So how do you find compression forms? Well, as far back as 1675, the British scientist Robert Hooke, the same scientist who formalized the physics of the spring, had an intuition at some point. He was writing a paper on helioscopes. And I guess while he was thinking about helioscopes, he decided that probably he could formalize, but maybe not with mathematics yet, that the shape of a chain that was hanging in tension had an equal and opposite relationship to an arch in compression, which means that the amount of tension in that chain in tension was going to be the equal amount of compression in that arch as it was standing. And so he wrote this in Latin, actually in an anagram. He hid this thing in a margin of this other paper. And he wrote, "As hangs the flexible line, so but inversed will stand the rigid arch." Now, at the time, there were no mathematics to prove this, and it wasn't proven until much, much later that this is actually true. But what it does is it sets out the basic attitude for how to make compression shapes. And this is the fundamental thing the fundamental property that actually guides all vault structures for thousands of years. And it's really quite powerful. And so it's something that I've really worked with intimately. It's something that I've also taught. So if you have the shape of a hanging chain, and you have a very strong material, brick is very strong material, relatively. It can be a very thin structure in that case. If you can put the bricks exactly in the shape of a hanging chain, you'll have a very thin and yet very strong structure. Now, in the case of a mushroom material, you have a very weak material. But using the properties of a hanging chain, and this can be confirmed with calculation methods such as graphic statics, by using simply more material in that shape, in that same shape, one can achieve the same structure. So a weak material needs a lot of material, a very strong material needs just less, that's all. And I would say if that material can be sustainable or renewable or even compostable, as this material is, then using a lot of it could be ethically perhaps better. Now, the arch is certainly a powerful tool, but then we can use the arch in interesting ways. This is something that I would teach even as far back as 2013. I did a workshop with students, high school students in Philadelphia. I taught them tile vaulting in 2 days, and they made these wonderful little dog houses that were very complex in curvature, but based on the principle of that hanging chain shape. This is also something that I brought. I was inspired by that project that I showed that was in South Africa, and I brought my own sort of ideas to Kenya in 2013 and worked with craftspeople there, interfacing with the way that they built and sharing geometries with them. So in an effort to make more efficient structures there on the island, but using their techniques. Here we're using compressed earth, using earth that we gathered there, basically right where we were building, mixed only with a little bit of concrete, compressed using that press. And we built this very, very thin tile vault. We also applied that shape to concrete. We made a very, very thin concrete vault, which turned into a radio station. Now, as we start to understand that the shape of the hanging chain, we know we can extend it even further. Masters such as Gaudi and Isler have used techniques that take this principle and extend it into 3 dimensions. What's wonderful is, of course, now we have computational tools, digital tools within the computer programs that we use as architecture students can help us find these complex and curving shapes. And simply by trying to understand how to build, then we can take for granted that a shape that is hanging can stand. One only needs to concern themselves with the thickness of the construction and the strength of the material at that point. So this vault was one that I built when I was a student between 2015 and 2016. And here the idea, we're using lightweight concrete, aerated concrete, so it's got like bubbles in it. And so we used this extremely lightweight material, and we said, how can we eliminate altogether almost the formwork, the necessity to actually describe that complex shape in space? So we used fiberglass rods then as a means of just visually delineating the shape, but everything else was basically the structure holding itself up. So the question here was, how do we take a flexible object and control that shape just enough to make something that will, in fact, stand? And so this project used then a combination of that flexible material and a very lightweight material. So this inspired then the process of this Mycelium Arch. We used, in this case, PVC pipes. We bent them into the shape of a hanging chain and fairly crudely put things together. This is using plastic and tape just to hold in this hemp material that had the mushroom already in it. It worked, except it didn't. And so, of course, construction experimentation requires failure. Otherwise, there's no progress. If something works, you have no idea what's going on. So you need something to fall down in order to know better what's going on. In this case, I was not present as the sort of master mason or master builder to observe the construction while it was happening. And so actually the arch was packed floating. One of the lower ends of the arch was not touching the ground. And so when we removed the structure, it settled and it changed shape. And because it was a weak material at that point, not in the right shape, it did in fact collapse. And so this was knowledge that I then brought with me into the context of the classroom. With some students at Georgia Tech, we worked on, I had a class that I was teaching structural design, structural form finding, in the context of computational design, and we applied those concepts to mycelium. So my students generated a shape using Rhino Vault, which is a plugin for Rhinoceros that you can download. I think it's free, in fact. And there is a new one for the current Rhino. And using very simple fabrication techniques with a laser, they were able to cut out several slices of this shape using cardboard, which is, again, it's cellulose. So it's a material that the mushrooms want to grow into and eat, actually bind and glue themselves to. And so they used this as an internal structure. And the idea was that, well, if this one collapsed, and you can see the bending here, we said, well, can we have some kind of reinforcement? If we're going to grow a lot of mycelium all at once, like cast concrete, are we missing something in this one that we could do here? Well, in fact, we know in cast concrete that we have steel rebar that we use as reinforcing. And so this was the first attempt at using a reinforcing system in a monolithic mycelium construction, well, or at least growing environment. What's fascinating is that because they had this digitally fabricated internal skeleton, the shape of the structure was exact. And in fact, my heaviest student managed to stand on it. He was about 80 kilos, and you can see it's only about 8 centimeters thick, which is rather wonderful. And so you have this extremely lightweight, extremely weak material holding up a person. And again, the methods are fairly primitive at this point. So again, cardboard is being used. Again, a waste material. I believe this cardboard was used as packaging for a delivery in the workshop there. So they used that. Here they are. So pulling the strands apart. So here you're seeing hemp that already has the mushroom in it. It's being pulled apart. We have to wear gloves because you can't. You want to try to reduce contamination of other organisms. And you can see very, very simply, just packing the material in. They're using plastic just to contain it, very, very crudely. And as such, it's not that attractive. I would say it's actually quite ugly, but fascinatingly so. But there's very important lessons, even in something that's quite ugly, which is that a three-dimensional shape does have more stability, certainly more than the two-dimensional hanging chain. And so there are more diverse load paths in something like this. And so you can actually have a little bit more imprecision in your construction by having a three-dimensional or a doubly curved shape. It's a little bit more forgiving. The internal skeleton was also extremely important. And so as we were thinking about going from something like this, which is like the size of a chair, to making something that's like, the size of a building, what do you do? And then the last thing is that we wanted to address the ugliness. We liked using a flexible formwork, but we knew we also needed some control. And so that experiment was exactly what we needed to basically make this thing. So what is this thing? It's an approximation of what I call a funicular fan vault. It's inspired by a British style of the Gothic. It contains nearly 3 cubic meters of mycelium, and it's a hemp based. So these are hemp stalks that are bound together with a fungus. The formwork consisted of plywood with some waterproofing membrane. That's to make the rigid formwork on the outside. On the inside, we used a woven geotextile to form those ripples that you see. Inside, there was a digitally designed and fabricated wood skeleton that we had inside of there. And so before I show anything else, I do have to say that, this work has been ongoing for a very long time, and it's not something that I've done alone. There are a lot of names, 2 universities, and countless hours of others that have gone into this work. And so I cannot go further without just at least having you read through a few of these names to recognize that, again, diverse collaborations are essential for doing work at all. And as architects, you will be collaborating with people, and better yet, you'll be collaborating with people who are not architects. And so I think this is important to just kind of put up there for a second. So the pavilion, I should say, was designed and built in the context of a seminar. So these were my students at Georgia Tech. Part of the project was we actually designed the thing. We designed it in the context of a music festival. So it was rather large. We, in fact, submitted this They had an open call for art, this music festival. We found one in the United States. They had an open call for art, and so the students made it even a construction schedule, when it was going to be put out, how we were going to put it up, when we were going to take it down, what we were going to do with it afterwards. And funny enough, the festival organizers emailed me back and they said, wow, this is wonderful, but we were just looking for paintings to hang in the woods. So maybe not this year, but we'd love to talk more. And we never heard from them. But luckily I had some funding. And in the end of the semester, we were able to construct this thing. Now, I should say at Georgia Tech, where I was doing my fellowship, the workshop where we could construct things was in a different place than the architecture school. And so from the beginning, the structure had to be more like a parade float. So it had to be on wheels so that we could push it. Here you're seeing us build that internal skeleton. The first night we worked quite late. Here you can see then the external plywood formwork. And at about 2 a.m, because we knew the material was arriving the next day, we started to push it down the streets of Atlanta. Of course, the police showed up because it was an unidentified moving object in the streets. Of course, these were campus police, and they were a little friendlier than what you might think of our police. And they actually helped us, stopping traffic for us. We had what we ended up calling the skeleton parade. In fact, it was the skeleton of the structure that paraded through the streets of Atlanta, only to be very ceremoniously packed the next day. Packing mycelium consists of using geotextile fabric and attaching it to the exterior plywood. There is a whole set of activities going on the outside of the structure that involve pulling mushrooms apart, introducing flour and water, and then giving it to, well, me and Sean, who were basically packing the whole thing here. It's a lot of work. It took a very long time. Of course, when you're working with students, they get hungry, and so we had to order food, maybe stop for some food, take a look at what we were doing, only to start back up again. Here you can see us at the top. We're beginning to fill it up, using that internal skeleton actually as a way of guiding the fabric on the inside. Now, 3 cubic meters is a lot of material to pull apart and pack. And remember that it is alive at this moment, so you cannot stop. It's worse than concrete. You can't stop. It took us 14 hours to pack this thing. I went home at 7 a.m. But it's really the experience. The experience is a part of it. The experience making it, of course, then the experience exhibiting it. Better yet, the experience of seeing a group of singers sing underneath it and tell you, hey, it sounded pretty good under there. So again, for me, I do these projects not to celebrate them, but to learn from them. So I'd like to at least spend the last little bit here to talk about some challenges that if you wanted to make a structure like this, things that at least from my own experience I can share, things that maybe you have to consider. And I'll break it down in terms of materials design, formwork, and reinforcing. Okay. So let's remember we are working with living materials. Okay. So that makes them extremely difficult to at least cultivate on a building site, which tends to be fairly dirty. We need almost a lab environment usually to grow these things. When they are dehydrated, like the top image here, there's a process of reanimation which takes several days, numerous hours, filling little bags with water and flour and letting them grow. There's an immense risk at that point because you can have infections and other things. If you use live material, so we used living material, it was bags that were already alive, shipped to us the next day from the company to my university. That was very expensive because they're wet bags. Imagine, again, agricultural waste full of water in bags being shipped the next day to you, several miles. They're in upstate New York, and we were down south in Atlanta. So it's quite a distance. So it's 1,500 kilometers at least. So that is something to consider. How do you get those materials? Are you cultivating them yourself? Are you buying them from somewhere and shipping them live? That's a huge cost. So these are things to consider right up front. Now, because they're alive, storing them is almost impossible unless you have a refrigerator the size of a building. If you're going to cast a building's worth of material, you have to keep them cold unless you use them immediately. We had almost 200 bags, and we had to use them that day, and that's why we packed for 14 hours, only to stop for some dinner in the middle of the night. Growing materials usually require clean environments, as I said, and so there's a lot of risk in doing what we did, to pack that much of a very expensive material outside where other things like mold and bacteria can just come and make their house right in our construction, is very likely. And then the last thing is that these materials need to be killed off, right? So it's actually very important to understand that we grow these materials and then we dry them. So when you have an object that's made of mycelium material, it's not wet at the end. We actually grow it, kill it, and dry it. And so when you're growing this much material, again, well, we had it on wheels, but we did not have an oven the size of a pavilion to push this thing into in order to dry it. If you're making a brick, you can put it in the oven, it's no problem. But here at the scale of architecture, you have to consider, especially when, at least using this technique, that you cannot dry actively, at least, a building-sized living structure. And so leaving them alive presents a risk of other organisms coming in and thriving in an environment that is, remember, wet, full of oxygen, and full of lots of food, sugar, cellulose, glucose, all of these things, really, really prime for mold and other bacteria. So these are very, very challenging things that have to do with the material itself. Now, remember, the material is very weak. So when you're designing something, you have to keep that in mind. Now, structures like these that are going to be made of mycelium will most likely be best in compression. And this is why I went on for quite some time about the shape of a hanging chain, as well as my vault structures, because, again, in this case, history will inform very directly how to use a new material, right? A very weak material, a material that has all of the limitations, we can actually apply historical concepts and actually make it work. Now, when you're dealing with thickness, however, because it's growing, it can be very challenging. 6 inches is approximately, what is it? Like 18, 20 centimeters? No, 15 maybe. Yeah, 15 centimeters. Anything thicker than 15 centimeters is very difficult to grow, because what you have is, through that construction, you have less and less oxygen. And so if you're wanting that mushroom to grow all the way through, you need to provide oxygen on all sides of your mold. So if you think about a mold, perhaps it's 5 sides, like to make a brick. The top could be breathing. The other sides are not breathing. So anything thicker than those 15 centimeters, at the very bottom, it may not be breathing and may not grow at all. So this is very challenging, because you have a weak material that must be thick in order to stand at long distances, but you can't grow thick if you want it to grow all the way through. So the optimization here is quite a challenge, but a lot of fun. And then the last thing is that the lifespan of these materials depend on their exposure to the elements. It's an open cell material, which means that there is air inside of the material. Mycelium is not a continuous surface like plaster. It's a woven, although very tightly, but it's a woven surface, right? And so over time, water, if it's exposed, will absolutely get in and make this corn or this hemp wet, and it will degrade the material. And I'll show you that. And so that has to be taken into consideration. From a design standpoint, how are you protecting the material, if at all? Do you use another material as a roof to protect this material? All important things to keep in mind. So the design of our pavilion, as I said, was inspired by the chapel at King's College. This was a sort of my own take on a British Gothic vault, at least. So at the time, it was the last vault shape that I could think of that I hadn't built. I'd built freeform, I'd built a cross vault, I'd built barrel vaults, and I'd never built one of these. And so it occurred to me in the middle of teaching this seminar that, wow, isn't it wonderful? A British fan vault is like a mushroom-shaped column cut up into pieces and rearranged. And I thought that, well, that's wonderful. So I gave that to my students, and that's actually how we came up with the shape of that thing. But again, it's still based on the principle. Here you have a column, something that can actually stand, a compression structure like this. Now, the mushroom shape was actually shaped as a partial catenary. So what happens is actually when I split this thing in two and I put them together that way, it actually makes a catenary in there. So it's the shape of a hanging chain. And as I rearrange the parts again, I just get that going in the other direction. So again, that shape is immensely important. But almost more important than calculating the right shape is describing that shape using formwork of some kind. As you saw from the picture with my students, the grains are loose when you're packing them. So it's exactly like concrete in that you pour it, or it's more like compressed earth, I would say. You compress it into the mold. The mold has to be strong. It needs to be able to support the weight of wet agricultural waste while maintaining the form. This particular plastic structure had some difficulty. You can see right here that due to the weight, and again, I was not here on this day to fix this, but they actually let this arch have this sort of misshape in here. And that was due to the flexibility of the formwork. So again, it has to actually keep the shape, or else you'll end up with a shape that's not strong. The other thing is that the formwork, if you would like to remove it, it cannot be made of cellulose. So wood is not allowed. You must use something like plastic or foam or some other material that the mushroom cannot eat. So that's something that's important. As I've mentioned, the mushrooms also need oxygen to grow. And so it is important that the mold that you make is porous. So for the pavilion, we used basically two techniques. Number one is that we used almost a very traditional form of concrete formwork. We used plywood with plastic on the inside. It's very common in concrete formwork. Also, less common, but well known, at least in the concrete arts, is the use of fabric formwork. And this was something that we were really very interested in using, in part because it was like the plastic that we were using. And it also was going to give us some kind of unknown quality on the inside. And so the idea was that we had then this plastic board that was laminated to the plywood. And we used that as a guide to attach that fabric. And then we could pack mycelium in there, right? So the substrate was going in there. And we could do that little by little. And so our catenary shape was very precise. This was cut with a CNC machine. And really, we learned how to do this just by doing some research. If you know anything about fabric formwork, Mark West is the master at this. And so what we noticed was basically you have to have a very rigid element and you can have a very flexible element, but the rigid element must hold the flexible element. And so in our own way, we just adapted this technique in order to make something for ourselves. These are some of the legs of the pavilion just 5 days after packing them. So it grows very quickly when it grows well. We use geotextile in this case because it's woven and it lets the material breathe quite a bit. Now, as I've talked about this internal reinforcing as well, an important consideration, but perhaps not essential. In our case, we were building something with a new technique at a biggest scale that we'd never done. And so this safety that you could get with reinforcing on the inside was essential. And so it's important to note, though, that whereas the exterior formwork, which was to be removed, could not be made of cellulose, the internal skeleton, you actually want that mushroom to attach itself. To me, this is more interesting than the relationship of steel reinforcing or steel rebar and concrete. We know that the relationship with concrete and steel rebar is very tenuous because after some years, that steel will begin to rust and corrode and cause weakness inside the assembly. In this case, the mushroom eats its way just a little bit and attaches itself fundamentally to the internal reinforcing. And so it's a pretty interesting analogy to take in the case of concrete, something that it does not like in steel, and in this case mycelium, which loves anything made of cellulose. So for the pavilion, we used what's called oriented strand board. So it's a panel product made of wood. There's a lot of glue. And this was a decision that I made because, again, this was a very big structure and we were going to put it in a public place and I was going to have students singing underneath it, and I could not take the risk. But at least in its production, we were able to demonstrate that, sure enough, a mushroom column does in fact make this shape, which was rather enjoyable to play out. And again, the internal skeleton in this case was another means for us to guide where we were putting the mycelium. And so the workplace looked a little strange, a little bit like a concrete work site, a little bit like something you don't really know. I mean, these people banging these bags against the ground, trying to break them up and mixing flour in here. And we have a mixer over there. As I said, there was a lot of material and we did have to invent ways of working that day. So as a team, we didn't know what we were doing that day. And so hour by hour, we were coming up with systems, means of communication, processes, quantities in order to make things go the right way, and little by little make it. And you know, it was of course a wonderful experience, but even more important because of what we learned. Now, when it comes to this internal reinforcing, I want to point out that it was made of wood, very, very strong, very rigid. As I've mentioned before, mycelium has air inside of it. And because it's made of a natural material, when humidity changes, when temperature changes, that material expands and contracts. The skeleton on this pavilion did not expand and contract with it. And so in Atlanta, where it's extremely humid, this material was expanding and contracting kind of extremely in its first month. And it started to develop cracking because that internal skeleton was breaking the membrane of the mycelium. And so what then transpired was essentially a process of decay. As it rained on the structure, as the temperature changed, it gets very hot in Atlanta, and then it dries up at night. And so this whole thing was expanding and contracting. 12 months later, I ended up, well, we took it down after 4 months. It was looking pretty bad. But I kept 2 of the legs, and I decided to keep them just to see what had happened. And what you can see is basically the degradation happened because Atlanta, it rains a lot. And what was happening was that water was running down the side of the column and accumulating. And so you can see that 12 months later, there's this circle right here, this oval maybe shape, where you can see that water has come in and damaged the material. So at first the mycelium was protecting, but then it started to act more like a sponge. I will point out though, from this bottom edge to here, we have full growth. So we did manage to actually grow a pretty decent thickness. So I'll just wrap up to talk a little bit about what's going on now, because after all, this pavilion that I'm talking about lasted 4 months and it happened in 2018. So as I mentioned at the beginning of the talk, that pavilion was done while I was doing a fellowship, and now I'm working in the capacity of a professor, and so at a different university. So I've been settling in for about 2 years, and I've finally managed to gain a grant, so gain funding to work on this here at my university. I'm working with a fungal geneticist and an economist who's specifically working in agriculture. And we are working on some fairly large topics that are dealing with the kind of economies of at least rural environments in the United States. And this is a platform that we're beginning to build where we're looking at the very, very small scale. So actually understanding the biology of how these mushrooms grow, perhaps look at their genetic makeup, and if necessary, to genetically modify them in order to give us more favorable material properties. So what we're trying to do is connect the very, very small the micro to the nano, even the molecular, and to connect that with materials that exist at the human scale. And so this is what we're interested in. And we know that, of course, this is a very big question. And so it does require studies and the creation of economic models that start to look at things like, where is the agricultural waste? How do you move it? And even if you did know which mushroom to grow in there, what could you make? And does it have a higher value than that waste just being compost? So these are very, very interesting questions that, of course, I can't tackle alone. And so these diverse collaborations are just underway now. Now, I'm also teaching a seminar on this topic, and this is some work that my students are working on now. We are working in a kind of extreme sustainability mode where we're using no plastics at all. So this is really drawing into question why we need to use plastics. And although forming the material is obviously necessary in order to use it, but perhaps questioning how we form. So one of my groups is looking at the use of weaving in basket weaving techniques to actually make the formwork in which they pack. Of course, because basket weaving is made of a cellulose material, the mushroom just grows right into it. And it's really quite fascinating. They're going to make a pretty tall column, something like 2 meters tall. Another group is using techniques of hanging fabrics. And they're hanging the fabrics and using gravity as a means of actually forming thin mycelium sheets. And so we'll see where that goes, but this is just a little peek. In my own lab, we're doing research that begins to look at the properties of mycelium and tries to associate them with acoustical panels. So in addition to being a mason, I'm also a musician, and I just have an interest in music. And so I've been working on an acoustics project for some time that deals in the use of a computational design methodology called shape grammars. We're using simulation, and now we're making panels out of mycelium, which is very, very exciting. We're also working on a number of commission projects in the lab and beginning to do research and development on that. We're taking this idea of a thin, flexible mycelium sheet and kind of taking it to the extreme. These are 2 extremely thin sheets, maybe 2 centimeters, 3 centimeters thick. These sheets that we pushed together, and they were pushed together while they were still living. So they were very flexible. We pushed them together, they grew into one another, and then we dried the whole thing. And what you get is then a rigid, extremely flexible objects. More sculptural so far, but again, working towards some commission projects. So again, I think we have to come back to this original question of, why is architecture to be permanent? If it is permanent, what are the materials that we should use? And if architecture is to be less permanent, to be temporary, can we start to think of new ways of building for tomorrow? So again, I'll just leave you with this question. It's one that's very important to me. It's what I think is necessary, not only for us today, but for really to have a sustainable life on this planet. We really need to think of the impact that we as architects have when we build things on the planet. So thank you so much for your time and for listening to me. I'm sorry I went for a whole hour. Mathieu, you said take your time. So I spoke a little slowly, I hope. But I'm more than happy to discuss at length to cover anything else, any questions that you have about the structure or about the future of this material. It's something I'm very passionate about, and I hope that after this, you too can be passionate about it. So thank you very much.
Thanks again a lot, Jonathan, for this very clear, explainful presentation, and taking it to a point that I didn't think about do we need permanent building for the future? That was not, this is not something that is even taught, or I guess, a lot in Turkey, or I have not seen, but we don't have so much, as I have seen, these kind of problems about, not yet, at least, breaking down all buildings, but we have earthquake.
Mm-hmm.
that are breaking down buildings.
Of course,
So
of course.
that's something really interesting to think. Yeah, why? What we do after a building is getting, we don't want it to be destroyed, but it might be.
It might be.
No, not destroyed, but at least not usable anymore.
Right.
Because of, even if it doesn't destroy, so then what we do with the waste. So
that's right.
That's the same thing. That's really interesting. So I'm really happy to hear your thoughts about it. It was really good and above it, knowing all of this fact about myceliums and how it is used and how we can use it. So thanks really a lot for it, and thanks to
my pleasure.
Take the time to tell us all of this during 1 hour is perfect. I mean, I was not bored at all, for sure. And at least one person was not, and Ebru had to left, my friend, but she wrote to me that she really want to finish to listen to it from the video because it was really good. So don't.
Oh, thanks so much.
And thanks again a lot. So.
Well, here, yes. I'll unshare my screen so we can maybe have a little bit more of a discussion, and I'll share it again if I need to reference an image. But yeah,
if
anything.
Anyone wants to open his video, so we really have a discussion and question, that would be really nice.
Yeah.
And we already have a
I see one in the chat. Do you think it can be used effectively in your country? Sure, why not? But you have to make it work, right? And you have to prove, right? So again, think back to this history that I told, right? I was talking at length about masonry and vaults and this Spanish guy, right? So how does he do it? This technology doesn't exist. And so he makes something to prove that concept that it works, and even proves that it can be better than the other systems that exist. So this is the challenge that we have when we want to make, I think, innovation in building construction. You have to invent something that is better than the existing system. So it has to be more sustainable. Yes. It has to be stronger, right? It has to last longer or last less, but then have no impact. So it's the ethics, I think, that come into it, but as well as convincing. Right? We have to change the building codes. Isn't it? You must have to build in concrete, right? In Turkey.
Yeah.
I'm sure it's required, right? So for certain constructions, the laws in which that we live in and that we are working as architects and designers, the laws that exist and control our work, prefer materials. And it's written. So part of what it is that we have to change the minds of the people who are writing those things. And the only way that we can do that, I think, is to prove it. Right? You can't do it any other way. But of course, Turkey has some agriculture. There is something made of cellulose that someone isn't using. Even if it's just for making furniture, that wood dust can be used, no problem. And of course, there is an edible mushroom that you could grow into that sawdust or wheat stalks, corn stalks, hemp stalks, anything, soy. You could grow it there. So really, there's no limit. And as I said, there is a company that sells this material in Europe. So I think you could even get some.
I have a question. I have some friends in Turkey that are growing mushroom. I mean, they are even selling those kits for eatable mushrooms. So
yeah,
they are basically the same, isn't it?
It's exactly the same. Now, there are some species of mushrooms that do this a little bit better. So you want a mushroom that is fairly aggressive in its growth. And so this tends to be what are known as the bracket mushrooms or the cantilever mushrooms. These are those mushrooms that you see on the tree, and they make those kinds of discs, cantilevers.
Like oyster mushroom would work.
Oyster mushrooms work wonderfully. Reishi mushrooms work very good. And so there's a whole class of them that are quite good. They love to eat agriculture waste, and they work quite well. And indeed, if you know a mushroom farmer, you're set.
Okay.
Just use his old bags. If he'll eventually have a bag that won't make more mushrooms, but it's a bag of mycelium,
Okay.
You're
Perfect.
done. You're
Good
done.
to know.
Yeah.
Okay, Mehdi, please.
Can you hear me? I'm gonna like I don't
Yes.
want to write it's gonna slow. My question is actually I have three questions, and one of them is about the current usage. The second thing is about the future of the material. And the third is like I want to ask at West. The first question is that you mentioned about this materials, how you use as a try to use it as a construction material, or try to use as like a vault. My question is that can it be used for kinetic facade? Because kinetic facades actually not a very thick layers. And is it mycelium flexible enough to be a kinetical facade member? So it will be used in major buildings.
It is not like a fabric. So we are using fabrics, at least now, to make sheets. But the thing to think about is that it grows and it's wet and extremely flexible. But then you have to kill that mushroom because otherwise it keeps growing and bad things happen. So when you kill it, the consistency of the material is like foam. You know this like pink or blue stuff? We put it in like our walls, right? Like medium density foam. It's exactly the same. The difference, instead of petroleum, it's just corn or hemp. So it's not flexible. However, as I've said, it's commercialized. People have been working on this 20 years. There's a company in the United States called Ecovative, and they have something that they're calling Microflex. And it is looking more like a flexible foam. Now, there are 0 products with this thing. I think they may have made like a small piece, and then they just took a really close video, right, to show it. But at this point, it is rigid. So you have to think of it as more, it would have to, if it were to be on a kinetic facade, for example, it would have to be within a stiff panel that moves, but itself, probably not. The flexibility, however, when it is alive, is rather compelling, right? And so I shared those last 2 slides of the kind of sculpture thing. And what I find fascinating there is, just like when you want to bend wood, right? You can kind of steam some wood and bend it. It has exactly that property. And so in the same way that we can form wood in strips or sheets, we can actually form mycelium, at least just this consumer stuff, exactly in the same way. So not great for facades, though, also because it's open cell. So again, it gets wet, it degrades. Unless you paint or treat, right? Like you could put some kind of protective material, and it would be okay.
As they did for the pavilion in Netherlands, no?
We did nothing.
No. The pavilion in Netherlands that has been built.
Oh yes, yeah. The guys in Netherlands, they're working on like some kind of a paint or like epoxy, essentially, that is inspired by like the Incas, right? So they're using, I don't know, berries or something. I don't know what they're doing. We were not so interested in that. For us, it was, the research was really about how do you even grow 3 cubic meters of this stuff? Your second question, though. I hope that answers your first one.
Yeah, it answers clearly, actually. And my second question is actually, I met this mycelium material for like, it's been a year. I learned this material last year. I'm very excited material, so I tried to use that material in my every design in the studio. And this year, actually, we are doing extreme architecture, which I'm focused on living in Mars. So my question is that, can mycelium, if we think about the architecture, philosophical question of architecture of Mars, can mycelium use on other planets? Because there's a new type of mushroom found in Chernobyl, which absorbs radiation. So I actually come up with a question, can it be used in Mars, or as an insulation or as a shell structure?
Yeah, so there are researchers at NASA right now who published, maybe you saw this report. They published one in like last year. It was beginning of last year, I think, maybe a year ago.
I didn't know.
And they published this report. Yeah, I mean, it was pretty, for me, it was kind of funny because they're talking about making these buildings on Mars, and they make a stool that's very ugly and a brick. That's like, so, you know, it goes to show what government funding goes to making, but at least here. But yes, so they're proposing, and I believe right now on Mars, there are edible fungi that are trying to be grown up there. And what their system is essentially making a mattress. So it's basically 2 layers of plastic, an inflatable, basically to produce the sort of force that you need to make that kind of a shape on Mars. And then they have a whole system of algae and other kinds of organisms that bring oxygen and nutrition. And so, yes, they're proposing to make a shell. I mean, I think it would be great, but those mushrooms would probably need to get killed off. The notion of keeping mushrooms alive anywhere is very dangerous because mushrooms need a constant source of food, and they grow toward their food. If there's no food, they get out of there. And so what happens is you could grow it for some time, but after some time, if that food isn't there to eat, they will do one of 2 things. They'll either break down and go away, or they will cannibalize and make new organisms or new compounds, chemicals, that would be potentially very, very bad. So the problem of Mars is huge. I think there's people who are extremely optimistic. I personally think we have lots of problems on Earth, and I think I think that maybe mushrooms are more useful on Earth than in Mars. But look, I think, you know, it's proof that if NASA's getting funding, that this is absolutely a real thing and it should be pursued. So I would say, if it's of your interest, number 1, go look at that report from NASA. You'll find it.
Do you have like a keyword? Do you remember it? Because I'm going to look at it.
I think if you say NASA, mycelium, done.
Yeah, I'm going.
It will be the first thing.
So what about, like you said, it should be killed off, but Mars surface is like minus 60 Celsius. Right. Will help is like it's frozen.
So yeah, actually, that's an extremely good point. Well, then of course, then you have to take into consideration the energy to keep it at 80 sort of room temperature, right? Mushrooms like it exactly the way that we like it to grow. They grow and thrive in humid, warm environments, not hot, but warm. So yeah, the energy that would go into even making those mushrooms grow in the first place. But it strikes me that you're right, then to be able to freeze them. Of course, the inner surface, of course, is then, if it's for humans, is going to be warm. So then you have a problem of warm, cold, and it could insulate, but then maybe you've half alive. I don't know. It's an interesting question. I haven't thought very much about it. Again, I read, you'll read it, and you'll see what people who are thinking about this stuff in space, what they actually made. I mean, I had to tell my students that it was ridiculous. I mean, I respect them as researchers and scientists, absolutely, of course. But it's a little funny, I think, the power that we can see as architects, people who can make things, the power of just proving it rather than speculation. And, you know, yeah, I don't know.
I think we should go to the next question, because there are a lot of questions also in the chat. So.
Oh, okay.
Okay.
Maybe you had a third question, or is it okay?
Yeah, I have a third question, but it's a short question. But I can wait if I can wait for the end.
Okay, as you prefer.
Okay, I'm gonna wait the others.
Can I ask?
Yeah, but one, please.
Firstly, thank you for presentation. I was thinking about the bigger construction with this material, and we see some examples, but of course I haven't experienced. I guess it is light material, and is construction destroyed easily if we make the construction with this material? For example, because of the weather conditions with a strong storm.
Yeah, it's absolutely a consideration. It's because, yes, it's foam. It's medium density foam. So yeah, I think, you know, as a structural material, this is absolutely something to be taken into consideration. I want to clarify that I am not promoting monolithic mycelium as even the way forward. I will not even say that monolithic is even better than using bricks. Okay. So I don't think mycelium is better than most materials when it comes to things like strength, storm resistance, permanence. But I think that in other contexts of construction, so other than long span, other than you know, something that needs to last forever or withstand a storm, there are lots of other kinds of human environments, structures that we need that maybe don't last as long, that currently we might be using things like plastic. And maybe it's better to use something like this, where temporary is okay. And actually temporary plus destroyable, better yet, compostable, becoming food for something else is pretty compelling for me. So I think the use and its applications are important to consider. Absolutely.
I see. Thank you. Thank you for the answer.
Thanks for that. And it was a question about, I don't know how to pronounce the name at all, so about 3D printing with fungi. Is it a thing? Is it possible?
Totally. Yeah, totally. So I'm not doing it yet, but there are absolutely some people who are making essentially a slurry or a paste that consists of exactly this stuff. So it's got the fungi in it, and usually then using sawdust, and they make a paste with flour, water, the mushroom, and sawdust usually. And if you're familiar with 3D printing with ceramics, right? So clay, you have like a tube of clay and then a nozzle, and then the machine just moves around. The 3D printing with mycelium is happening exactly with that. There's these Italians that are making these good machines, the wasp machines. Yeah.
Wasp machines.
Yeah. So you could get a wasp, and if you can invent the right paste, and there are absolutely papers that will tell you how to make that paste. Yeah, you can do that. It's amazing. Yeah, it's really cool. People are making small things though, like a vase. But really, obviously, a compelling idea because it eliminates the need for formwork.
Exactly.
In many ways.
And I had a question that in my mind. Okay, mushrooms, like fungi, I never truly believe in it as a construction. I mean, as a structural material. But the way I see is, as you say, it should be killed. But that's the reason why blocks are easier to use.
Yes.
But then to combine the blocks together, could you use also a kind of mycelium paste so they will grow on each other, something like this? I mean,
yes,
isn't it a thing that can help for solve some of the problems? But then it should be killed again, so I'm not sure it will change a lot.
Yeah, it's like an endless cycle. So yes, there's a process that people have called either myco-welding or bio-welding, which is essentially the process of taking two pieces that are living, putting them next to one another, and then the mycelium will grow across and literally connect. They fuse. And so absolutely, you can have a dry brick, have living mycelium, put it in between two dry bricks. It works. It's like not even difficult.
Okay.
But to your point, right? So then when you're talking about the masonry arts, then you're talking about formwork again. That paste that you're talking is not like gypsum, right? So I love tile vaulting because gypsum, it's like putting glue on there, right?
No,
It's
I'm
easy.
speaking about a wall, an infill wall.
Oh, a wall? Yeah, no problem.
Because I am thinking about, okay, you are thinking about future of architecture. I'm thinking about immediate usage.
Yeah.
If you have infill wall made of mycelium bricks, just like this, it's insulating and there's no structural anyhow. So it can be basically used anywhere, anytime. That's just it.
Or even as formwork for concrete. So in the same way that we use medium or high density foam to form concrete, or even to make insulated concrete walls.
Would it work? It's strong enough for this, for the holding the concrete.
Yeah.
Okay.
Yeah, I mean, you'd use it the same way, right? If you're using foam, you're using a lot.
Yeah.
Or you're backing it with plywood or something.
Yeah, sure. Okay, thanks.
Yeah. No, it's that's the thing. It's easy. It's just when to grow, how to grow, who has it.
Yeah. Yeah, this is another. This, of course, it's the source of the material is another question, but imagination of how to use it, then why not to find?
Yeah.
Okay. Yeah. Thanks. So, is there any other question? Anyone would like to ask something else to Jonathan? No, maybe you can ask your last question then.
Okay. My last question. Actually, it was when I learned about this material, it actually got my interest very much, and I actually sort of wanted to work on this material. But then the question that hit me in my mind that this topic becomes more scientific topic rather than an architecture topic, like design topic. So my question is that if I, let's say, want to work on this material or other things on this, should you have like do a bachelor or do a master in biology unintentionally, because it goes scientifically, not much more designing, but more scientifical. If I want to do it, what should I do?
I hear you. So I want to stress, I'm not a biologist. I actually got a very bad score when in university when I took biology. I did great in the lab, but the lecture for the tests failed. So no, I'm very bad at biology. But look, I'm a builder, right? So first of all, I think everything is a design problem, and there's nothing that you as an architect can't address, because you are able to address aspects of life in ways that other disciplines can't. The essential thing that we have that most other disciplines don't have is empathy. When we design a space and we design it for someone, we have to empathize. Actually, even when we design it for nobody, you still have to empathize with the thing that you're, right? So no, and remember my other point, you have to work with other people, right? So I know nothing about fungal genetics, right? Nothing, like zero. But I entered this field as someone who said, well, I can buy this little bag if I had lots of little bags, just like we do when we have concrete bags, right? If you want more concrete, you buy more bags. That's it. So I think this is ideally suited for architecture. Whether or not you actually make architecture, right? Also, architecture education is good for lots of things, more than just buildings. So no, I think if you're passionate about this, just do it. Get yourself some material. Here, I'm going to link this place in Netherlands where you can buy it. So I think you can get it from these guys, and just try a little bit. It sounds like your professor may have a mushroom farmer, so
I can give the link to you maybe.
Yeah, so if you can just get some, then just make a mold. Just try.
The problem was that my mother says that it's gonna smell a lot, so I'm not gonna let you build it.
No, but it smells like it's mushrooms that you eat. And again, remember, as a product, you're killing it off, so it doesn't smell like anything.
Then I can try them. Really.
You just have to try, and then you'll
just
know.
Do it on the balcony. The weather is good enough now to do it on the balcony.
There you go.
Well, actually doing the balcony is different because I'm living in Gaziantep, which Gaziantep has a high rainy. It's a very rainy city, so doing the balcony will be the worst thing, the first place to do it.
I think like anything, you won't know until you just do it. And again, I think for whether it's to validate for yourself or to validate to your mother, to whoever, just do it. Just do it. It's fun. It's fun.
Okay. I think thanks a lot, and we can finish with this perfect sentence. Just do it, try it is exactly what I'm trying to promote also in my classes. And so thanks a lot for telling it again, Jonathan. Just do it,
Absolutely.
try it, and you will see if it is working or not. And you showed to us that it is working for some usages. So thanks a lot again, Jonathan, for this really good presentation, and thanks to all of us for your participation to it.
Yes, wonderful to be here. Thank you so much. And yeah, please, if you have any other questions, reach out. Mathieu, you have my email.
Yes.
I'm also on Instagram and reply to people who have questions about mycelium. So don't be a stranger, and welcome to the community.
Thanks a lot, Jonathan. Have a good day.
Good night. Yes, thank you. Good night, everyone.
Bye-bye.
Bye-bye.